Hello and welcome to one more tutorial in this series on using the Arduino Uno with I2C LCDs. In this experiment, we'll be demonstrating a dual timer. We'll be using timer 1, but we'll be firing two interrupts parallelly. One would be the timer overflow interrupt and the other would be the output compare register interrupt, which fires when a value in register A matches the threshold value. So here's our setup. The MB102 breadboard power supply. Then we use jumper connections to power the Arduino, and the Arduino itself is connected to the I2C LCD. We look at the connections in a bit in detail. On the left are the jumper connections to power the Arduino. Then we have the A4 and A5 pins of the Arduino connected to the SDA and the SCL serial data and serial clock of the I2C LCD. We have the ground pin of the Arduino connected to the power supply. This is a good practice to do because this ensures that the entire circuit stays at the same ground level, and if you don't get this right, there might be errors. Although in this case we are powering the Arduino with a jumper connection, so it really doesn't matter, but still I would recommend it as a good practice. So here's the MB102 power supply with the 5-volt jumper connected. We then have the connections on the I2C LCD, the SDA, the SCL, the VCC and the ground. We did an experiment a short while back to scan the address of the I2C LCD, and we found out that in this case the LCD address is 0x27 or 39. You may have a different address in your experiment, but if you have purchased the same make, you would have the same value. It's very important that you use this value only in your code. If you use a different value, then the code would not work. So here's our shopping list, and some links to buy these on Amazon are provided in the description box. Here are the male and female connectors which we are using in this series of experiments to set the Arduino free. So what we'll be doing in this experiment is that on the top row, we'll be printing out a label called cycles, and after that there would be a value which gets incremented every time the timer overflow interrupt fires. Below that we'll have another value, and that value would be linked to the output compare register OCRA. Now every time the output compare interrupt is fired, instead of resetting the value, what we will be doing is that we will be updating the threshold value from say 5000 to 10,000. So what would happen is that the first time initially the value would be 0, and when it reaches the threshold of 5000, the interrupt would fire and the value on the LCD would get updated to 5000. Simultaneously we would update the threshold for the output compare register from 5000 to 10,000. So the next time this interrupt fires, it would fire on reaching a threshold value of 10,000. The value would not get reset. The value would count further from 5,000 to 10,000. It would get updated at 10,000 and then again at 15,000 and so on and so forth. So what we have here is that we have a timer which covers the timer overflow or a period of say approximately 1 second, and we have parallelly smaller interrupts firing off at say 1/4 of a second. So the practical application is that this could be used to do multiple sequencing operations of the kind that happens in assembly line. So this is a basic model which can be used to run experiments of that sort. So here are the code snippets. So first you would have noticed that I am using the unsigned integer 16-bit variables. So this is basically because we are using timer 1 and that has a maximum value of 65535. This variable would be large enough to hold this peak value. So first we have an unsigned integer called cycle. So this value along with this top row label of cycles, this gets printed in the top row. Then we have two volatile integers. Again, unsigned 16-bit integers. So one called top and one called bottom. So you can guess the purpose. The top is basically the one which is going to get updated inside an interrupt vector and will be used to update this cycle value which is there in the top row, and the bottom would be actually used to update this. It will get updated in the interrupt, and later in the void loop it will be used to update this count, which uh, helps to record the value in the bottom row. So here are the top row and the bottom row labels. We have an integer I. I'll just describe the purpose of this variable in a later slide. And we have a constant integer called update. So this is basically going to push up the threshold of the output compare register A. And so this is another volatile integer called OCR. So this is going to be used to set the output compare register value. Things would get a little bit more clear when we see the code in further detail. Now, why are we using volatile values? We're using volatile values because these values are getting changed inside an interrupt vector, and volatile values are stored in the RAM instead of storage registers, and that means that that's the right way to store a value of a variable which is getting adjusted inside an interrupt. So we come over to our void setup loop, and here we have the basis things. Initializing the LCD, clearing the LCD, turning on the backlight, setting the cursor to 0, 0 and printing the top label, that is cycles, followed by a 0, setting it to the second row and printing the bottom label, that is count. So this is basically the initialization part. After this, we will also have the timer 1 initialization, which we will describe in a little bit more detail. So now we come over to the first timer interrupt. So this is the timer overflow interrupt, which basically updates this volatile variable top. And right now we have basically rigged up the code to fire approximately every second. The prescaler is 256. So this fires approximately every second. And here's our void loop. So in case the timer overflow vector fires, then top gets incremented. So top would no longer be equal to cycle, it will be greater than cycle, and that would make the conditions inside this loop true. So cycle will be set to top, the volatile variable will be copied on to the normal variable, and this normal variable is then used for the further computations. So first step is to set the LCD cursor to just after the label. This is the label length, cycles is the top row label, we get its length, and set the cursor to just after that. And then let's suppose that the existing value of cycle is 10, then the value of I would be 2. So what we are doing here is printing 2 blank white spaces. It's not strictly necessary, but it's a good practice to do this. Just make sure that the part of the LCD where you're going to print, that gets cleared. So if cycle happens to be 100, then automatically I becomes 3 and you print 3 white spaces, clearing off the 100 and getting ready to print the next value, which might be 101 or 102. Then we set the cursor to just after the label, and now we are ready to type the updated value of cycle. So here's the other interrupt vector which fires on the output compare register value A getting matched. So the first step is that the maximum value that we can have is 65,000 because the upper threshold is 65536. So if the OCR value hits 65536, then bottom is set to 0 and the OCR value is set to update. Update was a constant integer. It basically stands for an increment of 5000 units. The OCR 1A value is set to this OCR. So basically when the code starts, so OCR 1A is set to 5000, and when it hits the peak, then OCR is again set to the update value of 5000, and the counter value, that is bottom, is set to 0. What happens in the other case? What happens is that every time this counter fires, the bottom is set to bottom plus update and OCR is set to OCR plus update. So basically the bottom is a value that is going to get printed, and this is the new threshold. So I'll just explain the example. Initially bottom is 0 and OCR is 5000, and when the timer interrupt fires, then bottom is reset to 5000 and 5000 gets updated to 10,000, and the value of 10,000 gets updated in the OCR 1A register, and the updated value of bottom, which is 5000, that goes into the void loop for getting printed. So here you can see that bottom is no longer equal to count. See, here we not use the greater than sign because we can have two cases. That one is that bottom, in this case, if we operate on this else mode, then bottom would be greater than count. But if we are here, then bottom would be reinitialized to 0 and count would be a much larger value. So we use not equal to, and in case this is true, then count is set equal to bottom. The cursor is set to just after the bottom row label, and here again the same trick of printing blank spaces and clearing of the existing value, and then we are ready to print the updated value. So now it's time for us to flash the code and see how this code works. So here's the code. I'll just run through it quickly once again. Here are the various variables that we discussed. Here's the setup, and you may notice that here the LCD backlight is commented out because it makes it easier for me to shoot a video. But under normal circumstances, you should be keeping this, you shouldn't be commenting this out. Then we come over to the timer initialization part. So this part I hadn't discussed earlier. So TCNT1 is set to 0. The timer is basically initialized to 0. We are not using any clear timer on compare mode. We are just updating the OCR value on our own. So TCCR1B is initialized to 0. And this value basically sets a prescaler of 1024. Here are the timer masks. You can notice that we have used or equal to set two timer masks to be true. The first one allows the timer overflow vector to fire, and the second one enables the output compare A mode to fire. Then the OCR 1A value, the threshold value, is initially set to update our constant integer, which is at 5000. Then we enable all the global interrupts. Here's the void loop, which I discussed just a short while back. And this is followed up by the timer overflow vector. And this is followed by the timer compare vector. You'll notice that in both cases, the timer loop is kept extremely small so that it executes quickly. It's time for me to flash the code. I select COM4 and flash it off. So codes are successfully flashed. I unplug my Arduino and I turn on the power supply. So you can see as soon as the power supply is turned off, look at the top row. The top row increments slowly, 1, 2, 3, 4. And in the intervening period, you can see that the bottom row goes 5,000, 10,000, 15,000 and so on till 60,000, exactly as we had programmed. So that's it for this video. Thanks a lot for watching and do subscribe to our channel. Thank you.